All right, guys, how's it going? Welcome back. We are going to do a lesson that is new to our Unit 16, but we're going to start off with the three most common functions that we know so far, those being linear, exponential, and quadratic. So what I would like you to do real quick as a do now is take these three different functions. One is y equals t. This is y equals 2 to the t minus 1, and this is y equals t squared. Three different functions, all representing the speed of a car. So t is minutes and y is in miles, so we're talking about accelerating a car. And I want you to change your window setting. So go into your window setting, which again is at the top of your calculator, and adjust your x min, x max, x scale, y min, y max, y scale. Then fill in all of these numbers. Take a few minutes to do that, and then we're going to go ahead and talk about those. All right, so if you went through and filled it out, you would get 0. You would get 0.2. So 0, 0, 0.2. Then we're going to get 0.4, and we're going to see a pattern here of 0.6, 0.8, and 1. Then we're going to come over here. We're going to see 0. We're going to see 1.1487, 0.31951. We are going to see 0.51572. We're going to see 0.7411 and also 1. And then the last one, we're going to see 0, 0.04, 0.16, 0.36, 0.64, and the last one is going to be 1. Now, right off the bat, we see that this guy is our linear function, this is our exponential function, and this is our quadratic function. So what we want to do is we want to first off talk about what are their graphs going to look like. So I'm going to quickly go ahead. If you want to pause the video, great time to do so. Again, all these values came from just adjusting our window setting and plugging these into our y equals function and grabbing those values that went with the inputs. If you don't know how to do that, you could always take these inputs and plug them in by hand or by calculator and get these outputs that go with them. But now take a minute, pause the video, and plot all these function points, and we're going to see what they look like. All right, so we're going to have 0, 0. We're going to have 0.2, comma, 0.2, 0.4, 0.4, 0.6, 0.6, 0.8, 0.8, and then 1, 1. And our function is going to be a straight line that kind of comes straight through there. All right, then we're going to plot the other one. We have 0, 0 again. We're going to have 0, 0 here. Now 0.2, I'm going to go a little bit past 1. That's 0.14. That's my fault. That is 0, my fault. So I'm going to go a little bit above 0.1. A little bit above 0.1 is going to be right here. And then I'm going to go a little bit above 0.3, which is going to be right around here. And then for 0.6, I'm going to go a little bit above 0.5, which is going to be right around here. And then at 0.8, I'm going to go up to 0.7, a little bit above it, and then 1, 1. So this one is kind of like bending up at the slightest bit. It's going to curve through here, but it's also going to converge here at 1. And then our last function is going to be the last one, which is 0, 0. And then we're going to have 0.04. So that's going to be really low here. And then 0.4 is 0.16. I'm going to go just above 0.1. 0.6, I'm going to come up to 0.36 right around here. And then 0.8, I'm going to go to 0.64, just above 0.6. And then 1, 1, it's converging there. Now this one is kind of bending up a little bit faster, but also converging at that point. So again, this one in the blue I put here, this is y equals t. The one I put in the red is going to be y equals 2 to the t minus 1. And the last one I did in pencil, this one is going to be y equals t squared. All right, which car has a constant speed? Now that's a key word. Constant speed means the rate of change does not change. So the only one of these that has a constant rate of change is our linear function, which is this one here, car 1. We will call this 1, 2, 3, just for the sake. We're going to call that car 1. But I know that car 3 is accelerating the most. Now it says explain your reasoning. The reason we know that this is accelerating the most is the fact that it was slower, 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 but it caught up to the other two to make it here. So this is starting to accelerate the fastest so that it could catch up at the same spot. All right, so in this course, you have learned about 3 types of functions: linear, exponential, quadratic. You guys know these 3 functions really, really, really well. What we're going to do today is we're just going to talk about different ways we can identify these 3 functions so that you know them even better. So finding the function is an important part of solving problems. What methods can be used to identify which function describes the relationship between the dependent and independent variables in a problem? So let's just recap really quickly. You guys already know that a linear function is when the degree of the function is 1, meaning the largest exponent is 1, typically in the y equals mx plus b form. Then we have an exponent that is unknown. When the exponent is unknown, in other words, the variable is the exponent, we have an exponential function, y equals ab to the x. And then lastly, we have our quadratic. That happens when the degree of the function is 2. The largest exponent is 2, and that's going to be quadratic. And we know the different shapes of these, but first off, let's just go through these 3. Take a second and write the word linear, quadratic, or exponential underneath each of these, and then we will see if you get them right. All right, remember, you can always pause the video and try these on your own. Since we have in the exponent an unknown, that is going to be an exponential function. In this case, since the degree of the function is 1, you could distribute the -2, add the 4, and go through that whole process, but it is not necessary. We know that this is linear. And since this is going to be x squared, we have an x squared. That is our quadratic. Awesome. Good job. All right, turn the page. All right, second type is we're going to identify them from their graphs. First thing we did was we identified them from their equations. Now we want to know what they look like. You already know linear is a line. Exponential is this curve that either grows very quickly or it can actually decay. Linear functions can also get lower if the slope is negative. And then we have our parabola, which is either pointing upwards or it could be upside down and going down. So again, just by knowing what they look like, you can identify if it's linear, quadratic, or exponential. So let's just take one quick example. Let's plot these points and just determine what shape it takes. Pause the video, plot these points, and then we'll go from there. All right, 0, -1 is here, 1, 2 is here, 2, 3, 3, 2. I could see it turning back down already. So this is going to be a parabola shape. And if it's parabola shape, then we know that this function is a quadratic function. In other words, if you knew the equation of this, or if you wrote it down, it would have a degree of 2. 2, the exponent, the highest exponent would be 2. All right. The last way we're going to teach you today how to determine if it's linear, quadratic, or exponential, not from its equation, not from its graph, but from a table of values. And we're going to use differences or ratios. Now, you guys already know this. if the x value, and you could read through this on your own, but if the x value goes up by the same amount and the y value goes up by the same amount, we say it has a common difference. We learned about those in our arithmetic sequences. If it has a common difference, then what is it? It is linear. It is linear if it has a common difference. You already know that. Awesome. If as the x goes up by the same amount, if you're multiplying by 2, for example, we would say this has a common ratio. This is a geometric sequence of numbers making this function exponential. Now you might say, okay, I already knew that, and you'd be absolutely right. This is nothing new. But let me introduce you to something that is new, and it's how do I tell if it's quadratic? Well, there are really two ways. The first way is to analyze if you see a turning point. So as the x values go up by the same thing, we notice that the y values will turn. So -1, -2, and it goes back to -1. That's going to tell me there's a turning point or a vertex, so that's quadratic. But the problem with that is you don't always see the turning point in your table. And there's another really cool trick here, and it's called the second difference. Let me show you this. All right, so from -1 to -2, we subtract 1. And from -2 to -1, we add 1. From -1 to 2, we add 3. And from 2 to 7, we add 5. So, does it have a common difference? Absolutely not. But watch what happens. What's 5 minus 3? We get 2. What's 3 minus 1? We get 2. What's 1 minus -1? We get 2. So what we notice is the second difference is constant. And when that happens, you know you're dealing with a quadratic function. So let's recap real quick. Linear functions have a common difference. Exponential functions have a common ratio. And quadratic functions have a constant second difference, the difference of the differences. And that will be true of every quadratic. All right, so let's practice a few of these. All right, take a minute, pause the video as always, read through these 4 examples, see if you can analyze just by the patterns if it's going to be linear, exponential, or quadratic. All right, awesome. So what we notice in the first one is that we are increasing by what? We are increasing by 0.5. Every time we keep increasing by the same amount. And again, these are also going up by the same amount. That's important. As these go up by 1, these are going up by 1/2. So this has a common difference. We would say this is linear. And if you said linear, awesome, you are exactly right. Let's go to this one. Remember, these are going up by the same amount. What do we notice? It looks like we're multiplying by 5. So we're timesing by 5 to get to the next output. Times 5, times 5, times 5, times 5. That's a common ratio. So I know that this function is a curve and it is exponential. Really good. All right, let's go down to the next 2. As these go up by the same amount, by 1, what is happening here? Well, this looks like it's multiplying by 2. Look at the pattern. Times 2, times 2, times 2, times 2. If it has a common ratio, we know that this is going to be exponential. And the last one, well, let's see. This is clearly not multiplication. We're not multiplying by anything. So let's check addition. So here I'm adding 2.5. I don't see a turning point, so I can't just automatically assume it's quadratic. But this is by adding 3.5. Okay. And then from here to here, it's 4.5. And then from here to here, it's 5.5. That's not a common difference, and it's not multiplication, so watch what happens. We're going to check the second difference. What's the difference between 2.5 and 3.5? 1. Difference between 3.5 and 4.5? 1. 4.5 and 5.5? 1. That is called the second difference. And when that is constant, the same number each time, we know that we have a quadratic function. All right, so I hope you got those. Let's go to just a few applications, and then we are going to be done with this lesson. Real quick, pause the video. I want you to match the function to the situation. Look at these three functions. One of them's quadratic, one's linear, one's exponential. Match it to its situation. Pause, and then hit play when you're done. All right, good. Well, I hope you noticed that since this has a square, that's our quadratic, and that's going to be this one right here. The ball is launched upward, and then guess what happens with gravity? You are right. It comes back down. That's a parabola. This has an exponent of 1, so that's going to be our linear function. The same amount's our keyword. And since our unknown is in the variable's in the exponent spot, that's our exponential. And it's doubling every month. How do you make a number double? You multiply it by 2. And guess what? When you multiply a number each time in a sequence, it is exponential. So C is going to be that one right there. All right, let's go to the last page. All right. The table shows the shipping cost C in dollars by weight W in pounds for items from an online store. So real quick, just analyze this information and let's describe linear, exponential, or quadratic. We are going to see that you are increasing by 2.5, and then you increase by 2.5, and then you increase by 2.5. When it goes up by the same amount each time, that is linear. Great job. Last question. I want you to analyze each table and match it to the correct equation at the right. Well, let's take a look here. We have 4 functions. I could see that this is going up by 4 each time. So that's going to be 18, 22, and 26. When something goes up by the same thing each time, we will call that linear. Now, come to the equations. Unknown in the exponent, that's exponential. I'm going to put a little e there. X minus 2 squared, that's quadratic. X plus 1 times x minus 3. Well, what's x times x? X squared. So you're going to have a second quadratic function. And mx plus b, that is our obvious linear function. So this is going to be r of x. Which makes sense because the y-intercept is 6, and the common difference is 4. All right, so let's eliminate the next one then. So the next one looks like it is turning here. How do I know that? Because it's 15 on either side. And this one looks like it's turning because it's 6 on either side. So these must be my 2 quadratic functions. So this is my exponential function. This is my exponential function, f of x. This must be f of x, my exponential function. And the pattern looks like it's multiplying by 6. So that's going to be 6, and that's going to be 216, and then times 6. You could always take these inputs and plug them into the function, or use your calculator and get your table values. So last ones, you could do these two to fill in the blanks one of 2 ways. First off, you could just look at a pattern. The pattern is 15 on either side, so then if this is 6, then this has to be 6. Now you might say, well, how do I then figure this out? Well, you could plug it into the function. You might say, well, which one is it? Well, the vertex is 218. Well, going back to last unit, what's the vertex? This is in vertex form. This has a vertex of 218. And these have roots at -1 and +3. -1, 0. Remember, 0, 0, and 3, 0. So this must be g of x. That's my quadratic function g of x. And this is my quadratic function h of x, since the vertex matches the vertex. So you could take these inputs and plug them in. And if you did that, you would get -9 here. And if you plug in 4 to g of x, you would get -10. All right, so let's just wrap this lesson up. We have our takeaway. How can I tell the difference between linear, exponential, quadratic using a table? Why do I say that? Because that's really the newest thing today. You already knew that the equations are in what form they are. You know first degree linear, second degree quadratic, and if there's an unknown in the exponent, you know that's exponential. You already know the three shapes. You know linear is a line, exponential is a curve, and parabolas are your quadratics. So what really is new today is that second difference. So if there's a common difference, it is linear. If there's a common ratio, it is exponential. And if there's a common second difference, that is the newest thing for you today, then it must be quadratic. All right, so you have a few problems to work on when it says justify using differences or ratios. We just want you to talk about these things. So when you get to your assignment there, you also have Castle Learning and practice, practice, practice. That is the best way to get good at math. Keep up the hard work, guys, and we will see you next time.